Thank you, Boy. That was very good. Very interesting. So just things that we saw from Boy's presentation is that when you adjust for things in a multivariate model, you could get different associations depending on what variables you put in. And it does depend on what you really want to know from your model. But we also saw that it's important to model variables appropriately, because if we'd have modeled age as a continuous variable, we would have got the wrong association for age with STI prevalence and incorrect adjustment in the final model. So what you want to know from your model will determine the model that you ultimately want to develop. So we said that you want to know the independent predictors of the outcome after adjustment, or do you want to quantitate the odds ratios for different predictors as measures of risk, or do you want to develop an equation to predict the probability of the outcome? There's different model checking strategies we can use, and three very common ones are goodness of fit tests. And goodness of fit tests are like chi-squared tests, because what we do is we compare the expected and the observed number of events, usually categorized by deciles of risk. And a p-value greater than 0.5 indicates that the model adequately fits. Another thing we can do is we can compare the area under the ROC curve, and that helps us in knowing how well the model discriminates between people who have the outcome and people who don't have the outcome. And the last very useful thing we can do is compare models using likelihood ratio tests and information criteria. Now, these things can be used for model selection within your own model, but they're most important when you're developing a predictive model that you want to apply to other populations. And in this kind of situation, if you had a big data set, you would divide your data set into a testing data set of about 70% of your observations and a validation set of about 30% of your observations. You would test and develop your model in the testing data set, and then you would validate that you got the same results when you applied it to your validation data set. An even better thing to do is to use your own data set and then apply it to an external validation data set from another source. Now, I mentioned information criteria, and these are criteria based on information and entropy, which is randomness. And models are penalized in different ways to select the best model. Two very common ones that are implemented in most software packages are the AIC, or the APACC information criteria. And this would select the model with the greatest amount of variation explained with the fewest variables. The other one is the BIC, which is based on Bayesian probabilities, and that selects the most probable model given the data. And with both of these criteria, lower values imply that the model is a better fit. So let's have a look at the goodness of fit for the first model that we presented. And across the top, we can see that we've got groups. In this case, there's only been 9 groups developed because of ties. And you can see the probability, so increasing risk of probability of having an STI. We can see the observed number of events and the expected number of events, and the observed number of people who don't have an STI and the expected number who don't have an STI if we apply that model. And then you can see that the expected and the observed numbers are quite close across all of the deciles. And we look at the Hosmer and Lemechaud goodness of fit test, and we get a probability of 0.55, which shows us that the model fits adequately. We can then generate an ROC curve for the model, and we see the area under the ROC curve is 0.7 0.3. Now, the area under the ROC curve is the ability of the model to discriminate between outcomes. So if we picked randomly a person out of our data set and applied our model, based on our model, we'd have 73% of correctly classifying them as to whether they had an STI or not. Then for this model, we can also look at the AIC and the BIC. And when we're just looking at a single model, it doesn't tell us much. But I'm just showing you the AIC here is 219 and the BIC is 241. So now let's look at the second model. So the second model was exactly the same, except now we included age group. And again, you can see the observed and expected number of people who had an STI and who didn't have an STI. And again, you can see that the expected and observed numbers across the groups are predict quite well. And again, we see that the Hosmer and Lemarchow goodness of fit test indicates the model of fit is adequate. This time, the area under the ROC curve is 0.76. So we've got a 3% increase in the discriminative ability of this model to classify people as having the event or not. Now we can compare the AIC and the BIC for these models, and we see there's a slight increase in the AIC and the BIC for these for the second model that included age group, which would indicate that the model fit isn't quite as good. But actually, if we can compare the probability or the probability based on the log likelihood ratio test, then it's 0.3. So it's saying that really the models are quite equivalent in their predictive value. Now, I just want to have a think about this, and what, again, some of these data are just made up. I'm using sex from the multivariate model and some other variables just to show you. So this is a plot of an odds ratio with an x-axis on a log scale. So we've got the no effect value for a ratio of 1 shown as a red line. So if we look at male versus female, we see that the males had an increased risk of having an STI in our data set. And the confidence intervals go from 1.1 to 3.8. So that means that we have a p-value of less than 0.05. Now, if we put in another completely random variable like born in summer or winter versus spring or fall, then we see that the odds ratio is approximately, the level of effect is like 0.9 with wide confidence intervals. And because it's crossing the no effect value, then we also get a non-significant p. If, though, we were going to model something like consistent condom use that wasn't in our data set, but I've just made up a variable, and we see the odds ratio is 0.4 with confidence intervals going from 0.1 to 1.1. Because it's crossing the no effect value, the p is not significant at 0.07. But based on the confidence intervals, we see that the confidence intervals are most consistent with the decrease in the risk of an STI if you consistently use condoms, which is also biologically plausible. So when we're interpreting models, it's very important to consider the effect size, which in this case was our odds ratio, and where the confidence intervals lie with regard to the no effect value. And in the scientific and medical literature in the last 2 years, there's been a very big shift from journals letting people say that less than 0.05 is statistically significant, to really asking people to think about what are the clinical implications of my findings based on my effect sizes and my confidence intervals. And another good article to refer to is this one from the American statistician and the retired statistical significance article that was in Nature. And both of them really say that decisions should be based on p-values alone. And that's not, if you base the decision on the p-value alone, it's not good science. You need to consider the plausible range of the effect based on the 95% confidence intervals. And even the New England Journal now has introduced a policy where they won't let you report p-values for anything except your primary outcome. So if we look at our multivariate model now for STI associations, and this is a model that includes age group, we can see that there is an effect of ethnicity. We also see that the males have a higher risk than females. The ATS use group has an increased risk of having an STI, but the confidence intervals are quite wide. Alcohol use is also associated with an increased risk. Age group, we can see the effect of age group with the increasing odds of having an STI. And even though it's not significant, there's one group in our model that does have looks like they have a reasonably significant risk of having an increase of an STI, which is those aged 20 to 26. You can also present your data in other ways. So, for example, after you've developed a model, you might want to generate the predicted probabilities of having an STI by different variables in your data set. And here we can see the probability of having an STI by race, by age group, and by whether the person uses alcohol. So translating the data back into probabilities is quite useful as well for people to imagine the significance of your model. And here I've just presented it in a slightly different way, where we can see the risk of males and females having an STI by whether they use amphetamine type substances and the number of lifetime partners. So the conclusions from today, your model is a way to help you understand your data and explain it to others. The purpose could be to explore associations, quantitate risk, or make predictions that could be used, sorry, in different populations. So there's different approaches that you could use. A very reasonable approach is to include terms in your model if they're significant at less than 0.1 in a univariate analysis. It's also appropriate to adjust for known or suspected confounders. If you want to compare models to see whether those terms really impact on the fit of your model, you can do that with information-based criteria strategies. Don't forget that variables should only be modeled if there's a biologically or sociologically or other explanation and it's plausible for the association with the outcome. And more observations equals more power. So look at the odds ratio and the 95% confidence intervals, as well as the p-value, to interpret your model. I just want to finish with this quote by George Box, who was a very fantastic statistician. And he said that essentially all models are wrong, but some are useful. And I think a model is useful if it helps you to understand your data and explain it to others. Thank you.